Okay, so we've been talking about polygons, triangles, and special triangles, special features of triangles. And then at the end of last class, we started talking about circles. So I want to point out some special features of triangles that we've discussed that are going to pour over into our circles. And draw that a little bit better, maybe. If we have an isosceles triangle, so those two upright sides are the same and the bottom is a little bit different. Remember, an altitude is from a vertex and it goes till it's perpendicular to the opposite side. So we need to, the vertex that we need to use in our isosceles triangle is the vertex between the two equal sides. And to go perpendicular to the opposite side, it would be like that. We also talked a little bit about an angle bisector. An angle bisector cuts an angle in half. That would be cutting this angle here in half. And then we talked about a median. A median cuts a side of the triangle in half. All of these have one end point on a vertex of the triangle and one end point on the opposite side. And what we found in an isosceles triangle was that if we had an altitude, it was also an angle bisector and a median. In other words, if we knew that thing that we drew in was perpendicular to this opposite side, we knew it cut this angle in half and we knew it cut this side in half. And of course, the inverse was true. If we knew it cut this angle in half, well, then we knew it had to be perpendicular and it had to cut the other side in half. Or if we knew it cut this side in half, we knew it had to be perpendicular and cut the angle in half. If we knew it was one of those three things, then it had to be all three of those things in that isosceles triangle. And of course, it was also true in an equilateral triangle because, well, all three sides were equal, so it could be any vertex of an equilateral triangle. Then we started talking about circles. And there are several special things in circles that we want to talk about. Let's start. We brought up the idea of a chord. And a chord is just a line segment with its end points on the circle, or it's a line segment that connects 2 points on the circle. Now, that chord cuts off an arc out here. Now, I need to talk a little bit about those arcs and how they're defined. So if I have this arc out here, to define that arc, I could give it a length of it, but to get the length of it, I would have to know the radius of the circle, or the diameter of the circle, one of the two, and I would have to know the central angle. Now I'm going to signify that central angle, it's the Greek letter theta. It's used for an unknown angle. So if we have that angle in there, the length of the arc is equal to the circumference of the whole circle times that angle over 360 degrees. It's a fraction of the full circle. Whatever that angle is over 360 tells me what fraction of the full circle's circumference that arc is. But there's another way we could define it. Let's say that I tell you this angle here is 58 degrees. Now remember, this piece here was called a central angle. we can define our arc based off that central angle. The arc, sometimes referred to as an intercepted arc, because it is cut or intercepted by that central angle, is going to have the same, since its size is determined by the central angle, we can just describe it in that term. We can say it's a 58-degree arc. So going back to our chords here, if I have a chord on my circle that cuts an arc that's 72 degrees, and let's say that chord happens to be, let's go 9 inches long. If in the same circle I have another chord that's also 9 inches long, the arc that is cut out by that chord is still a 72-degree arc. Equal chords within the same circle will cut the same arc. Now, if I know that that circle has a radius of r, I have another circle that I don't know what the radius is, but I know it's the same radius as this circle. They both have a radius of r. In this circle, if I have a chord that's 9 inches long, that's still a 72-degree arc. We've talked a lot about similar figures, similar triangles in detail, but we've talked a little bit about other figures being similar, where they're just enlargements or reductions of another. Well, circles don't have too many defining features. We said they had two, the location of their center and the length of the radius. Well, if two circles have the same radius, the same length radius, the only thing that can be different is the location of their center. So by definition, they're not just similar circles, they are congruent, they're equal. So the pieces of one will be equal to the pieces of the other that have the same dimensions. Well, as we talk more about these chords, there's another rule of chords that we actually hit on last semester, but I want to go over it again just to make sure you remember it. It deals with chords that intersect in the circle. I should add the word interior because they intersect inside the circle, so they are interior intersecting circles or chords. And looking at the length, if this piece here is 4 inches and this piece here is 9 inches, if I know that this piece is 3 inches, I can find how long that piece is if I call that x, because those intersecting chords cut each other into pieces that have the same product. So this chord is cut into pieces that are 4 inches and 9 inches. 4 inches times 9 inches is 36 inches squared. You know, this other one already has a piece of 3 inches. The other one is x. So 3 inches times x is just going to be 3x. Inches if you want to keep the label on it. To solve that for x, we would just divide by the 3, or the 3 inches. 36 divided by 3 is 12. Inches squared divided by inches is inches. Over here, the 3 and the inches divide out, we just have x. So this is 12 inches. We used this last semester when we talked about arches. If I had an arch, let's say that we know that's going to be 36 inches across that doorway. And we knew that this piece here, that this was, let's go 9 inches high. And I wanted to find the radius of the circle that produced that arc. Well, we drew in this other piece here that along with that one, created the full radius. And we found that dimension. The 36 here got cut into 18 and 18. 18 times 18 equals 9 times x. 18 times 18 is 324, equals 9x. And we divide by 9, giving us 36 equals x. So x here is 36 inches, giving us a diameter of 9 plus 36, or 45 inches. And then, of course, a radius, which would be half of that, of 22.5 inches, or 22.5 inches. So that's the radius of our circle. So that used this concept up here of those intersecting chords having to cut each other into pieces that multiply up to the same product. But now there are a couple of other concepts that applied here that we haven't specifically talked about yet. And these are those properties that relate back to that isosceles triangle. Let's say we have a chord down here. Like that. I'm going to draw my radii from the center to each end of that chord. So I know that these two pieces are equal because they're both the radius of that circle. If I draw in this line here that is perpendicular to that line, at least this portion of the line from here to here, is an altitude of that isosceles triangle. And so since it's perpendicular, since it's an altitude, that means it cuts this side in half. That's what we needed to know up here to cut that 36 into two pieces of 18 inches and 18 inches. And of course, we also know that it cuts this angle in half. For right now, that's not going to be terribly important to us. But as we go to find areas of certain features, that'll allow us to turn different triangles into right triangles so that we can apply our trig to them. So one way we found, if I give you this circle, it has a radius of 8 inches. And I have a central angle here, make this a little bit closer to the center. Central angle here of 70 degrees. This intercepted arc, as we said, is 70 degrees. The length of that arc is based on the circumference of the circle. So the circumference of that circle is 2 times pi times the radius of 8 inches, otherwise known as about 50.24 inches. So the arc length is that circumference of 50.24 times that angle of 70 degrees over 360. So I have, come on, turn on, there we go. 50.24 times 70 divided by 360 gives me 9.769 inches. That's the length of that arc. If I have another central angle in that circle that is also 70 degrees, that arc length is also going to be 9.769 inches. If I have another circle, and that other circle has a radius of 8 inches, and I have a central angle of 70 degrees, that arc is also going to have a length of 9.769 inches. No matter where we put the 70-degree central angle on that circle is going to cut an arc the same length. And if we have another circle with the same radius, again, that same central angle is going to cut an arc the same length. Now, it seems silly to point this out, but we can use this to our advantage. Let's say that we know that this 70-degree central angle cuts that intercepted arc of 9.769 inches. And let's say we know we have an angle over here, 20 degrees. And I want to know its arc here. Well, rather than go through the whole process of finding the circumference and doing the circumference times diameter, the arcs are just going to, the ratio of the arc lengths is going to be the ratio of the central angles. So I have 70 degrees to 20 degrees. The 70 degrees was 9.769 inches long. We can cross multiply and divide 9.769 inches times 20 degrees divided by 70 degrees. So times 20 divided by 70 gives us 2.791 inches for this arc. So the central angle, the ratio of the central angles tells us everything we need to know about that arc. Okay. One other rule that's very important for doing many of our calculations is if we have a tangent line here. We'll put all the letters in there. So this tangent line is remember, a tangent line, all the points on the line are outside of the circle except for one point. One point is on the line, and all the other points are outside of one point is on the circle, all the other points are outside the circle. Well, a radius of the circle to that point of tangency, there will only be one radius that goes to that point. It will be perpendicular to that tangent. Mainly because that tangent going through, the two angles have to be equal, so they have to be right angles. But also, if I put another tangent line here, tangent to the circle at a different point, and draw it so it intersects this first one. From the point of tangency to where they intersect, those lengths are comparable. If I draw this in here, I've got another right angle there, right? And I know that this radius and this radius have to be the same. All the radii of a circle are the same. If I connect this across here, that has to be equal to itself, right? Every line is equal to itself, so that's two sides of a right triangle. Because there are right angles here, it's a radius on a tangent. If two sides of a right triangle are the same, because the triangle has to go with a squared plus b squared equals c squared, the third side has to be the same. So this length from the point of tangency to where they intersect has to be the same as that length from the point of tangency to where they intersect. These rules kind of combine towards, it's more so in machining than in woods, but a common thing working with round stock is to use something called a V-block. So you have that round stock sitting a V-block to hold it stable while you work on it. Well, if I know that this angle here is 58 degrees, and I know the radius of my stock here, well, I know that radius has to be perpendicular to the tangent. In other words, wherever that round stock is sitting in the V, where it touches the V is the point of tangency. So I know that radius has to be perpendicular. I know that this length has to be the same as this length. I know that if I cut this down through here, not only is that the same length, but it cuts this angle in half because it forms two equal triangles. So this is half of the 58. This is 29 degrees and 29 degrees. So now we have right triangles where we know the right angle, we know another angle, and we know two of the sides. We can find the other pieces of that right triangle. Let's start looking at those arcs. We said that a central angle here, kind of flying along today, sorry about that. A central angle here determines the size of the arc. So if we have a 35-degree central angle, this is said to be a 35-degree arc. That's what the arc is defined to be, whatever that central angle that intercepts it as. But there are other types of angles that we can have in our circle. Let's put a little bit bigger angle here. Let's call this an 80-degree angle. That makes this arc out here 80 degrees. Again, as always, that central angle and that intercepted arc have the same degree measurement. But there's something called an inscribed angle. An inscribed angle, if you remember, Tuesday, the inscribed angle has its vertex on the circle. Instead of at the center of the circle, it's on the circle itself. The size of that angle is going to be much smaller than the central angle would be. In fact, it ends up being exactly half of the intercepted arc. So that intercepted arc is 80 degrees. This inscribed angle is 40 degrees. And it doesn't matter where it is. It can be just off like this. That angle is still going to be half of the arc. It's still going to be 40 degrees. Or it could be up here. That angle is still going to be 40 degrees. We can use this for finding equal angles if we need to. If I tell you that this is a 15-degree angle, because they both of these inscribed angles intercept that same arc, this has to also be a 15-degree angle. Any inscribed angles that intercept the same arc have to be the same angle, same size angle. So that's 30 degrees. And of course, in the same circle, just like with our central angles, let's say I have another arc here that's 30 degrees. I have another inscribed angle off of that arc. This is still going to be 15 degrees. All features within the circle held constant. If the arc is the same, the angle that cuts that arc has to be the same. So we've got angles at the center of the circle, central angles. We've had inscribed angles with their vertex on the circle. What if the vertex of the angle is not on the circle or at the center of the circle, but it's somewhere inside? In other words, we have a scenario something like this, where we have two intersecting chords. And I'm looking at this angle here. Of course, those two angles have to be the same, because just looking at intersecting lines, remember, those are what we would call vertical angles. They're on opposite sides of intersecting lines, so they do have to be the same. If that intersection was at the center of the circle, and I'm going to draw my lines in here parallel to the existing ones. If they intersected at the center of the circle, this arc and this arc, of course, would be the same. They would both be whatever that angle measurement is. But as I slid that point of intersection over, if I slid those both lines over like this, you'll see that this arc became larger and this one became smaller. The amount that they change is actually the same. So the angle here that we are looking for is just the average of those two arcs. So let's say I tell you that this arc over here is 18 degrees, and this arc over here is 74 degrees. This angle in here is going to be found by doing 74 plus 18 over 2. 74 plus 18 is 92 degrees. Divided by 2 is 46 degrees. This is a 46-degree angle on each side here. So I'm trying to find this angle here and this angle here. Of course, they're the same. If I know that this is 24-degree arc, and this is a 194-degree arc. Now, half a circle, if I draw my diameter, half a circle would be 180 degrees. That makes sense. A little bit more than half the circle. This angle then has to be the average of those two arcs. 194 plus 24 over 2. 194 plus 24 is 218 over 2, which gives 109 degrees. Is that angle? This rule can also work backwards. If I know that this angle is 32 degrees, and I know that this arc here is a 28-degree arc, and I want to find this arc over here, which I'll call x. I know that x plus 28 degrees divided by 2 has to equal the 32 degrees. It has to equal that angle. The average of the two arcs has to equal the angle. And now we can solve this to find the second arc. We would multiply both sides by 2. X plus 28 equals 64. And we would subtract the 28. X equals 36 degrees. .36-degree arc there. We talked about secant lines. Secant angle or exterior angle that we talked about. So if we look at this, obviously if this is a central angle, that central angle and that outside arc there are going to be the same. So let's say this is 88 degrees. This is an 88-degree arc. If I drew it back to here, so it's an inscribed angle, this inscribed angle would be half of that arc, in this case 44 degrees. Well, this angle out here is smaller than either of those. It has to be smaller than the 44-degree inscribed angle. How much smaller? Well, that depends on how far. The further I pull it out there, the bigger, as long as this big arc, the 88-degree arc, stays the same, the further I pull this angle out, the bigger this arc gets. So that arc actually tells me how much smaller this angle is. So let's say that this arc here, let's call it 24 degrees. To find this angle out here, it's actually the half of the difference of the two arcs. So I have the 88-degree arc here. I subtract the 24-degree arc. And I divide that by 2. 88 minus 24 is 64 degrees. 64 divided by 2 is 32 degrees. So this angle out here is going to be 32 degrees. that can also work backwards. If I know I want this to be 28 degrees, and I know this is an arc of 96 degrees, and I want to know what does this arc have to be. Well, I know that 96 minus x divided by 2 has to equal 28. I can multiply both sides by 2. 96 minus x equals 56. And now we got to be careful here. We're going to subtract 96. Negative x equals negative 40. And now we divide by negative 1 to get rid of the negative 1x. X equals 40 degrees. So that's a 40-degree arc that's there. All these different rules kind of pile on and come together. If I have a diameter of a circle, it cuts an arc of the circle. Two ways to think about it. That's half the circle, so it's got to be 180 degrees because the full circle is 360. Or you could look at it as this diameter being a straight line has a central angle of 180 degrees, so that has to be a 180-degree arc. An application of that seems to be disconnected, not connected to it, but actually would be this. Let's say I have an inscribed angle that has its the endpoints of the arc that it intercepts are on a diameter of the circle. What does this angle have to be? Well, because this is a diameter of the circle, that makes this a 180-degree arc. That means that angle has to be a right angle. It has to be 90 degrees. Any inscribed angle that's inscribed on a diameter has to be a right angle. That would be a right angle. Up here would be a right angle. Any inscribed angle inscribed with its sides on the endpoints of a diameter has to be a right angle. Now, this gives us a lot to work with. I drew that poorly. Let me try that again. I need one more piece here. I gotta figure out where I want to put it. We will do it right there. So I am going to tell you here that this is a 32-degree arc. And I'm going to tell you that this angle here is 36 degrees. And I'm going to tell you that one more piece here yet. I gotta change one little thing. Sorry, the old hamster's not getting on the wheel real well today. This is where I wanted this to go, is down here. Just like that. Okay. So I'm going to tell you that this arc is 82 degrees, and that this angle here is 61 degrees. I want to know what this angle is right here. I want you to look at that for a couple of minutes, see what you come up with. Then we'll go over it. There's a couple of little subtle things in this problem that help you figure out the answer. Now, there's a lot going on here. So what I recommend you do is, if you have to, redraw the circle with only the pieces you need. The first thing, though, that I notice is that there's a right angle here. That right angle intercepts this arc over here, this one way over here. That tells us that this has to be 180 degrees, which means this is the diameter of the circle. Next, we look over here. We have this angle is 61 degrees, and this arc is 82. If I draw another circle with just those pieces in it that make that angle and that arc. So this is 61 degrees, 82 degrees. What I can find from that is this arc over here. I call that y because I'm already using x. I know that y plus 82 degrees divided by 2 equals 61 degrees. The average of these two arcs gives us that angle. So I'll solve that by multiplying by 2 on both sides. Y plus 82 equals 1, 2. We will subtract the 82, get y equals 40. So this is a 40-degree arc. Coming back over here, labeling it, this is a 40-degree arc. Well, now we have everything we need to know to find our angle x out here. We have this angle and that angle, or the two arcs, I should say. If I redraw that, I have this is an 82-degree arc. This is a 40-degree arc. And here's my angle. Well, it's simply going to be 82 degrees minus 40 degrees over 2. 82 minus 40 is 42 degrees. Divided by 2 is a 21-degree angle. So this is a 21-degree angle. So the most difficult part of all this is picking things apart and figuring out what pieces apply to what it is we're actually trying to do. The 180 degrees here for this arc didn't help us any with what we were trying to do, but it was something we could see rather quickly from the picture. Well, looking ahead, we are really close to done with this unit, with unit 2 here. So on Monday, there will be a quiz. Also on Monday, hopefully as many of you are in the classroom as possible. I want to make sure we look at grades, make sure everybody knows what quizzes they're missing. Almost everybody has at least one or more quiz missing right now. I think there's only one person that has everything turned in at the moment. So we'll have that quiz, and then we're going to finish up this unit, which means Tuesday, we're going to do two things. We're going to start Unit 3, and then we're also going to set aside 1 hour class on Tuesday for the Unit 2 test. Obviously, you'll get more time to finish it if you need it, but we're going to have that 1 hour set aside for you to work on it so I'm available to answer questions as you need it. I will post that quiz by the end of the day today, so it's out there so you can start working on it early if you would like to. Right now, homework. Go to the big book. Pages 626 through 629. Exercise 25-5. Page 631 through 633. Exercise 25-6. Page 636 through 638. Exercise 25-7. And page 643, 647, exercise 25-9. So we have about 25 minutes here left to work. If you would like to work on these, I'll be online here to answer any questions. Otherwise, that is all of our new material for today.